I give anybody an extra sheet?
Yeah.
There it is. I knew I counted it. I thought I counted it right. Okay, so if we look at number 1 here, this says to determine the specific heat of a new metal alloy. We've got 0.15 kilograms of that substance which is heated to 400 degrees Celsius. And then it's placed in a 0.2 kilogram aluminum calorimeter cup, which contains some water here, 0.4 kilograms of water, which is at 10 degrees Celsius. We mix those things together, the final temperature becomes 30.5 degrees. We want to know the specific heat of that metal. Okay. So basically, a calorimeter is a container of fluid that is insulated from the surroundings. For us, it's going to be a styrofoam cup. Okay. Nothing very fancy. The ones they use in camera much better, I think, than you would think our little cups are. But basically, you're going to have a cup. Sometimes you'll have a cup inside another cup to insulate it from the surroundings. You'll have a lid. You might have something to stir it with, a cap on top, all these things to kind of keep it insulated. When we look at these, we don't need to worry about the stir, the lid, anything like that. And in the lab, it's really just going to be a cup. For problems that we're doing on paper or in the book, just really kind of treat this like we've got a container of fluid here. It's water. It's at what temperature to begin with? Yeah, 10 degrees Celsius here. This is our water. We have a heated mass that we're going to drop in there. This was originally at, was that the 400 degrees Celsius. You're going to put them together, and you can draw another picture if you want to with, you know, the mass in the container now, and then show the final temperature of 30.5 degrees Celsius, like this. And we don't really need to show anything else. It's nothing more than us just putting a mass into a fluid here, in a cup or whatever it is. And we're assuming here that all the energy is being transferred between these things right here. That we're fairly well insulated, and we're not losing heat through the walls of the container, out through the top, or anything like that. So when you do these problems, we're talking about heat and this kind of heat transfer. Heat transfer due to a temperature change or a phase change. You really just need to identify any mass that's in the problem and if it undergoes a temperature change or a phase change. And then you need to account for all of those cues. So the first thing you should do with these is always just draw a picture if you need one, but then really just write down. We have the metal alloy, we have water, we have the calorimeter cup, and I'm just going to make a list of our variables for each one of these. And I think you really should, at the beginning, just slow down, decide on some variables, pick some subscripts for notation, and get everything straight with all the different masses. Okay? I'm just going to choose 1, 2, and 3 for each of those 3 masses because I'd rather write numbers than subscripts of a C or a W or anything like that. Okay. But you really could put water, you could put aluminum, whatever it is if you want to. It's just, I think, easiest for me to write numbers instead of those subscripts. Okay. And then just say, okay, what kinds of Q do we have for any of these? Are these undergoing phase changes or temperature changes or both? They're all just temperature changes. Okay. And we'll see that we could also do this with ice also. Let the ice melt. So we can have other forms of Q in here, but this one will just be all due to changes in temperature. So once you know that, we know we're going to be using this form of Q. So write down all the variables that you need for this equation right here. So we're going to need things like the mass, the specific heat, the initial temperature, the final temperature, and then we can also maybe write down our delta T. Okay. And I'll put a delta T1 on that for now. So the mass of the metal, we know. This was the 0.15 kilograms. The specific heat you can look up in a table for things that we know. This one we don't know, so you just leave that blank. That's what we're trying to solve for. This starts at a temperature of 400 degrees Celsius. Do we need to convert that? No, because our C's, our specific heats, are going to be in units of joules per kilogram per degree Celsius. So that's how we know we're okay to keep those in Celsius. But with the ideal gas law that you guys were just doing last week, those all had to be in Kelvin. Okay. The final temperature we know is 30.5. These mix together and all become 30.5 degrees there. Okay. What's the temperature change for T1 here? Which is? What's wrong with that? Has to be negative. Be very careful when you do these in your head. This might have been harder to do in your head because of the 1/2 or the 30.5 there. But if this was 40 and 30, you all would have done that easily in your head, I think, and just told me 370 pretty quickly. Because then that's how you do the subtraction. Just make sure that you always do these final minus initial. And you remember the negative if you're having a temperature that decreases here. If you forget that, then everything's going to be wrong. So just make sure you always do these in those correct orders there. Always final minus initial. Don't just subtract the smaller from the bigger and write that number down. Okay. So for water, we're going to do the same thing. The N2, I think we know that's 0.4. The specific heat of water is 4186 joules per kilogram per degree Celsius. We have the initial temperature of water is 10 degrees. The final temperature is 30.5. And the change in temperature, and I'm going to put 2's on here for all these T's, is 20.5 degrees Celsius there. So just get all this sorted out first, and then we'll worry about the equation in a minute. So N3 is our cup. That's made of aluminum. That is 0.2 kilograms. We have a specific heat of 920 for our C3. We also have the same initial and final temperatures we had for the water. So at the beginning, the cup and the water have come to equilibrium. They both have the same temperature. Everything at the end has the same temperature, but these both, the water and the container, start at 10, as long as you've given it some time for them to come to equilibrium. So we've got an initial and a final of the same 10 and 30.5. So our delta T3 is 20.5 degrees Celsius again. You really should take the time to write this out, because we're going to have different masses, different C's, different temperatures. Just take the time to write these out, and we're going to need all these to get all of our Q's for these 3 different masses. Okay. What we're going to do then with the Q's is, we know that energy is conserved. Okay. And our system is really just these things right here. Okay. Now, if we were losing energy to the surrounding room, then we'd have energy going from here to the water and then maybe heating up the room also. But this is all inflated, so we're just looking at these things right here. For conservation of energy, we just say that the sum of the Q is equal to 0. Okay. That's the form of the equation that I'm going to use when we start to set up these problems. Okay. But what this basically says is that your Q lost is equal to Q gained. So which mass would be my Q lost? Which one is losing energy or transferring energy away from it? Yeah, the metal. So what's lost by the metal is gained by the water and the cup. Right? So you'd have your Q for the alloy is equal to Q for the water plus the Q for the cup. Okay? Conceptually, this is very useful to understand. That energy is just lost by one and transferred to the other. Okay? When you do problems, though, I would set it up this way. both of these are statements of conservation of energy. Okay? Energy just being transferred back and forth between these things right here, with no energy lost to the surroundings. Okay? In this equation, what we really just do then is say Q1 plus Q2 plus Q3 is equal to 0. And that's the way I want you to set it up, because I think it can avoid maybe making some mistakes and confusion with some of the plus or minus signs. Okay? And then this really would just be M1, C1, delta T1, plus M2, C2, delta T2, plus M3, C3, and delta T3. Okay. I'm going to write it out that way this time, just to kind of show the way you'd plug it all right in there. Now, in situations like we have right now, my Q2 and my Q3 are both numbers that I could get with this data right here. And if I wanted to plug them all in right now, I could have just had some number of joules here and some number of joules there. But they don't always work that way. Sometimes you need to solve for something inside of here and just get in the habit of knowing that you can plug it in like I'm doing right there. Okay? I'm going to show you a little bit more about this equation and why I think it's not as useful later on, and I'll come back to that. Just for now, kind of leave that off on the side. We're just setting up right here with this equation. And then it's just algebra. I mean, that's how you set up the equation. Sum your q's, set it equal to 0. In this case here, we don't need to worry about choosing the plus or minus sign for the last early gain, because that comes out of the delta t. So if you just plug it in here, don't worry about the plus or minus sign, trust that they will come out from the delta t's, then you just do the math and now it's just an equation. You guys can solve that for any variable in here. In this case, we're just going to solve for this c right here, the c1. So we get negative m2 c2 delta t2 minus m3 c3 delta t3. Divide that by m1 delta t1. This will give me c1. Plug all our numbers in and we'll have our answer. And then I'll write all the numbers in here if we need to see them. We've got mass 2 of 0.4. We have a C2 of 4186. That delta T is 20.5 minus the mass 3, which is 0.2. And we're just plugging all these things in here now. Mass 1 is 0.15. And then we have negative 369.5 for that delta T. C, the specific heat, is positive. It should come out to have units in joules per kilogram per degree Celsius. All these minus signs you'll see will cancel out, so we're okay with our positive quantity here for C. Plug all these in though, and we will get 687 joules per kilogram for our C1, joules per kilogram per degree Celsius there. Okay. And you can see on here that there's a kilogram and a degree Celsius here and here, same thing here and here. That will cancel out with the kilograms and degrees Celsius on the bottom, leaving us with just the joules per kilogram per degree Celsius on top. Can you get that number? Those of you who tried plugging it in already? It's really all about this right here. This was, in my mind, one of the easier ones to start with, or just it's easier because there's no phase changes. But you identify all the masses, account for all the Q's you have when they are temperature change Q's. Then you don't need to worry about plus or minus sign. You just do the math and it will come out to the right thing. Okay? Let me talk about this equation here for a minute. And what I'm saying right now is only if you're kind of reading the book, looking at examples, just to kind of give you a heads up about what you might see. if I do this in the Q loss is equal to Q gain form, and I start here, I would have had to say that my Q loss would be for the alloy, right? This would be my Q1 is equal to Q2 plus Q3. This was the alloy losing energy, transferring it to the water and the cup. Right? And so that's something you can probably figure out easily here which one was lost or gained. Okay? When you do this though, you're going to see that this equation right here really should be absolute value. Okay? This is the amount of energy lost goes into the energy over here. And so if you put this in over here as M1, C1, delta T1, you have to keep that in absolute value. Okay? And if you don't, you're going to get the answer wrong. You won't have the right answer for your delta T. And sometimes you might just be off by a minus sign if you forget that. Other times, depending on what you're solving for, you'll have the wrong number. Okay? What you'll see sometimes is that when you do this, you can write that as M1 C1 times T naught 1 minus T1, which is initial minus final, which is not what you would think when you have a delta T. And in the book, you will sometimes see them write this out in examples because they're just making it positive. If I do it in this order, that value comes out positive, which is really the absolute value of this. But you might sometimes feel like, well, you don't know why. Sometimes it's final minus initial, and sometimes it's initial minus final. The order just gets switched sometimes to make that term positive. I don't want you to have to worry about that. You don't have to worry about that if you put it in the equation in this form. You don't need to think about which one is lost or which one is gained. You can just put it all into the equation, keep it all over here, and solve that equation. This is the easier way to approach it with the math. You have to think maybe a little bit less about the concepts, and you don't need to determine what's lost or gained. And there's no chance of you mixing anything up over here because it's just some of these Q's will equal 0. And if it's plus or minus, we'll tell you if it's lost or gained. This is always final minus initial if you do it in this form. If you do it over here, sometimes it might feel like you're switching things. Okay, this is not wrong. You can do it this way if you want to. And a lot of times you might see an example in the book or someplace else. Start in this form right here. Because conceptually that's what's happening here. What's lost by this one's gained by that one. And that might make more sense when you kind of think about it in terms of what's happening, but to do the math, I think it's better to have it in that form. Okay, so choose either one you want, but just know that if you're kind of reading through some of the examples in the book, you might see things like this and not know why. Now I'm telling you why, but you won't have to do that if you stick with that form. Okay. You don't have to choose the signs for those Q's, but this one you do. So we'll have to be aware of that when we get to those problems for changing phase.